Hi everybody, this is Mrs. Ewald signing in, and today I'm going to go through half-life. Now a lot of you may already remember half-life from math. I'm sure you fondly remember that, and may have some familiarity with it. So first off, we've already gone through in our first podcast for this unit what radioactive decay is, and also going through the different types of decay, so alpha decay, beta decay, gamma decay. And so you understand that you have something that's radioactive, and so when you're dealing with half-life, we're dealing with radioactive material. And so the half-life is kind of like a radioactive clock. So if you were to define half-life, it is the time needed to decay, or for decay, of 1/2 of the atoms in a sample of a radioactive material. And so you've learned the process of how you could go from one atom and have it decay into another atom. So that would be radioactive decay. So it could either send off a beta particle or it could send off an alpha particle, so like a 4,2 helium or a 0, -1 beta. And so what we're looking at now is specifically how much time it takes for this process to happen, but to look at 1/2 of those atoms to decay. So every radioactive element or isotope is going to have a specific half-life. Now the longer it sticks around, the more hazardous it is. So the longer the half-life, the more time it's going to be there, let's say in the atmosphere. The shorter the half-life, the less, I guess you could say, it's going to be sticking around. So therefore it's not as hazardous, but it does depend on how harmful it is when it is there. So let's go through an example. Carbon-14 is going to decay into nitrogen-14. So this would be like an example of a beta decay. Remember, the mass number is not changing, but what is changing is your proton number, so you're changing your element. And it has a half-life of about 6,000 years. So it sticks around for a very, very long time. And we could use carbon-14 for radioactive dating of things like rock and fossils. So this means that half of the carbon-14 atoms will decay in 6,000 years, approximately. Assume we start with 1,000 atoms of carbon-14. So let's use a table here to kind of go through this idea. So in the years past, 0 years go by. You have 1,000 atoms of carbon-14, radioactive material. It is going to decay, but it has not gone through its half-life yet. So we have no presence of nitrogen-14 atoms yet. We have the full amount of the original, so 1, or 1 out of 1. Now let's say you have 6,000 years go by. Okay? Now what's going to happen is you're going to have half of the number of your carbon-14 atoms. So that will be 500. The other half have decayed into nitrogen-14 atoms. So you would now have 500 atoms of nitrogen-14. The fraction of the original would be 1/2. And that means then we have 1/2 now of nitrogen-14. Another half-life goes by, so another half-life. Now it's 12,000 years later. We're now going to have half of our carbon-14 again, so that would be 250. And now we're going to have 750 of the nitrogen-14. Remember, both of these will constantly total up 1,000 atoms, so we're accounting for all of it. Now we have only 1/4 of the original amount because we now have 3/4 nitrogen-14. Another half-life, so 18,000 years later, half of 250 will be 125, and then the rest of it will be nitrogen-14, so that's 1/8 now of the original. And now 24,000 years later, we're going to have 62.5 atoms of our carbon-14 and 937.5 of the nitrogen-14 atoms. Now, also understand too, you can't really have half of it, so it would be approximately 62 or approximately 937, you know. And so now we have 1/16 of our original amount. Now, one way of going through this is you could go and say, well, you know, you have so many half-lives, you could go through and do it like this, and then figure out how much of your nitrogen-14 you have, or how much of the original amount that you have. But we actually have an equation that we could use and that is that the amount remaining is equal to 1/2 raised to the n, where n is the number of half-lives passed multiplied by your original amount. So, if I wanted to figure out my amount remaining after so many years, I could use this equation. So my amount remaining is going to equal 1/2 raised to the n. So how many half-lives occurred here? It would be 1, 2, 3, 4. So 4 half-lives occurred. So it would be 1/2 to the 4th, and my original amount was 1,000. So that is the amount of carbon-14 that I had originally. So what I could do is take 1/2 to the 4th multiplied by 1,000, and you should end up with something very close to 62.5. So that tells me how I can mathematically calculate, rather than going through trial and error, how much is remaining of my carbon-14, so this is of my carbon-14, after 4 half-lives. Okay? So let's go through some other types of examples. I want to go through one of it each, so you have that for when you do your practice problems in class. So here are some problems. Notice we do try to make them very realistic, like barium-122. This is something that you might use in an experiment. Also, you might use it for medical reasons. So barium-122 has a half-life of only 2 minutes, which is why it's great for experiments, or also too for medical reasons, so it doesn't stick around forever. And you have a fresh sample that weighs 80 grams, so I'm just going to identify some pieces here. Oop. Let me go back to my board there. Okay. And it takes 10 minutes to set up an experiment. Using it, how much barium-122 will be left when the experiment begins? So this is very realistic, because let's say you do work with radioactive material in an experiment, you need to know how much you need to buy, because guess what? By the time you actually get it, you're only going to have so much of it left. So you do need to overbuy. So let's write the equation. Amount remaining is equal to 1/2 raised to the n multiplied by your original. And let's think about what we're solving for. We want to know how much will be left when the experiment begins. So we want to figure out our amount remaining. So we need to then figure out what our n is and the original. So how many half-lives occurred? So we know that it takes 10 minutes to set up an experiment, and it has a half-life of 2 minutes. So that would be then 10 divided by 2. So 5 half-lives will occur by the time you finish your experiment or have that ready. So that would be 5. And our original amount, you have a fresh sample of 80 grams. So now we'd be able to figure out how much is remaining. So 1/2 raised to the 5th times 80. You're going to then figure out that your amount remaining is 2.5 grams. Okay? So even though you started with 80, that's how much you need, you're only going to be able to have available 2.5. Here's another example with iodine, which is also used for medical reasons to look at thyroid and such. If 10 milligrams of iodine-131 is given to a patient, how much is left after 24 days? So the half-life is 8. All right, so again, using the same equation, amount remaining is equal to 1/2 raised to the n. So I could really just, I don't even have to show the caret, times the original. So we have 10 milligrams of iodine. How much is left after 24 days? And it says the half-life is 8 days. So we want to know how many half-lives occurred. So first we need to solve for our n. So we're going to take 24, because that's how many days after, and each half-life is 8 days. So that means 3 half-lives had to occur. So this would be 1/2 to the 3rd. My original amount is 10 milligram. That's what was given to the patient. So then the amount remaining is going to be 1.25 milligrams. Okay? Now, here is another example solving for something slightly different, and again, very realistic. So kind of going back to the idea of carbon dating, remember we said carbon-14 has a half-life of approximately 6,000 years? Well, this is the exact half-life that you would use for biological reasons. And it is used to date archaeological objects, because if you're able to date the rock, you're able to date whatever was inside the rock, approximately plus or minus 1,000 years, which is pretty good. So, in this question it says, all living organisms have a constant carbon-12-14 ratio. When the organism dies, the carbon-12 levels remain constant, but carbon-14 decays. So the changing carbon-12-14 ratio can be used to determine the date of the artifact. For example, if you have some fresh charcoal made from a tree that contains carbon-14, which will give a radioactive count of 13.6 disintegrations per minute per gram of carbon, prehistoric cave paintings were found in Spain. So if a piece of the charcoal found in the ancient cave in Spain gave 1.70 disintegrations per minute per gram of carbon, from this information determine the age of the cave painting. So we're going to again use the same equation, amount remaining is equal to 1/2 raised to the n times your original. And let's think about what we need to figure out. So we need to figure out, if we want to figure out the age, we first need to really figure out how many half-lives occurred. So we first need to figure out our n, because we do know that each half-life is this many years, but we want to know how many half-lives occurred to figure out our total amount of years to then calculate our age. So what I would do is, let's think about, it tells us that originally fresh carbon is going to have 13.6. So that would be the radioactive count. So that would be our original. And what they found in the cave was 1.7. So that's how much it decayed into. And so what we could do is now solve for n, how many half-lives occurred. Now what you could do is you could do a little trial and error. Otherwise, what you could do is do some algebra. So I'm going to take this and divide that on both sides. So I will end up with 0.125 equal to 1/2 to the n. Now if I want to solve for my exponent here, there's a few ways of doing it. Again, you could do trial and error, or you could take the log of 0.125 over the log of 0.5, get my n then, which is about 3. So I know that 3 half-lives had to occur in order for me to go from this many disintegrations to this many. And I know that each half-life is 5,730 years times 3. So that means 17,000 years, 190. So 17,190 years old, plus or minus 1,000. Really? That's pretty good. So those are some examples of half-life. You're going to be going through more of them in class. Make sure you're able to solve for any one of those unknowns, amount remaining, n, original. Doesn't matter. This is Mrs. Ewald then, signing off, saying happy half-lifing.